This is a practice final for UCLA Math 31B, Calculus 2. This is a practice problem set given by a professor back in 2023. So regardless of whether you have this professor or not, if you're currently taking a class at UCLA, hopefully this will be a good problem set to practice. And there are some challenging problems, in my opinion, on this problem set. If you came from a different video, I think I solved problems from like 2024 exam or something like that midterm. In the comments for those videos, there were multiple comments, I should say, that the problems were way too easy, and they were like shocked at how easy they were for an exam at UCLA. If you're in that crowd of audience, hopefully this problem set can satisfy you. There's some more challenging problems in here. They're not like impossible, but for sure a step up in level from the ones that I shared and worked out previously. All right. With that said, hopefully that was not too long of a blurb. Let's begin. Number one. So I would recommend that you try these problems first on your own. I purposely have the question set here. I would recommend you pause the video to try it first on your own and then unpause it to see the solution and how I thought through it. No guarantees that my solution is 100% correct, though. I just want to throw that disclaimer right away. Okay. So go ahead and try this first on your own. I'm going to assume you tried it by now if you paused the video. So let's go over it. Number 1A, this is a true, false, and a short answer. Number 1A, is it true or false that there exists a power series with interval convergence 0 to infinity? This is false. So let me ask you, where's the center of this power series? It's impossible to locate the center. The center is always in the middle of the interval convergence. Where's the middle between 0 and infinity? It's impossible to tell. So that's one way to think about it. Another way to think about it is if one of the endpoints is going to be infinite, that means the radius of convergence is infinite. So that means this other endpoint has to be infinite as well. Radius of convergence is from some center, it goes radially outward in both directions. So if it's infinite in one direction, it has to be infinite in the other direction as well. So it's impossible for there to be such an interval of convergence. And as I was saying, where's the center? Well, in this case, even though it's not really technically the center, if my understanding of infinity is correct, but you can kind of imagine the center of negative infinity and infinity is 0. Okay, that's part A. What about part B? If this guy converges, summation as n goes into infinity, a sub n converges, then so does an squared. Probably for this one, it's easiest just to think of a counterexample. This is false. For example, if we know that this guy converges by the alternate series test, but if we square the sequence, it becomes the harmonic series, which diverges. Okay? This one, again, probably easiest to think of a counterexample, and here's one that disproves that statement. Part C, if an x minus 1 to n converges when x is equal to -4 and diverges when x is equal to 6, then n equals 0 to infinity, a sub n 2 to n converges. Is this true? Is this false? This is true. This is, again, testing the concepts about interval of convergence, okay? So what value of x is this guy from this guy? What value of x makes it this? It's when x is equal to 3. Okay, we're going to pay attention to that. X is equal to 3. So now the question to answer is x equal 3 inside the interval of convergence? Okay. Where's the center of this power series, by the way? It's when it's at x is equal to 1. Okay. So it's gonna the radius convergence goes radially outward from 1 Okay. That's what I said over here. Center is 1. So let's assume that this x is -4 is at the endpoint. It tells us it converges. Okay, let's assume that's the boundary at the endpoint. It stops at this endpoint. So what's the radius of convergence if that's the case? It's 1 minus -4, which is 5. So this is kind of like a worst case scenario thing. the radius of convergence is 5. So if that's the case, this is the worst case, is x equal 3 inside the radius of convergence? It is, because if the center is 1 and the radius is 5, that means the other endpoint is 6. 3 is for sure within the interval minus 46, right? Negative 46. So it's inside the interval convergence. So yes, it converges. Okay, remember at the endpoints of the interval convergence, it could either converge or diverge. That's why we check the endpoints in those types of problems, if you remember. So it makes sense that if R is 5 for this to converge, but this diverges, they're at the endpoints. Okay. D, if an x minus 2 to n has radius of convergence 2, what is the radius of convergence of an squared x minus 2 to the n? Okay, so honestly, I didn't think of any shortcut way to do this. Maybe there is one. Feel free to share in the comments if you know. I just used the ratio test. Okay, ratio test says it converges when it's less than 1. That's how we find the radius of convergence, right? So if we go through the algebra, these simplify, and it's a constant because it doesn't depend on n, so we can pull it out. Or it's like a constant, I should say. Okay. And we can divide both sides by this limit. So that's what I did over here. It's given that the radius of convergence of this guy is 2. So that means this guy, this term over here, must equal 2. Okay, that's how we always determine the radius of convergence, right? We isolate the absolute value. Whatever is over here is the radius. Okay. So this guy is equal to 2, which means the limit is equal to half. We're going to use this and use the ratio test again on this guy. Sorry, my computer is somewhat laggy. You're going to have to deal with it with me. Okay. So ratio test on the other guy. Go through the algebra again. These simplify like before, but then we have this over here that's remaining. We can actually rewrite it as this squared. Okay. Why can we do that? Well, if you square something, it's already positive, right? So either you absolute value it first, and absolute valuing is also making it positive. So it doesn't really matter the order, okay? The reason I want to write it like that is because I can divide both sides by this square term, right? And this we know the value of, it's half. So 1 over half squared is 4. The radius of convergence of the other guy is 4. Okay, hopefully that made sense over there. Definitely if you need to reread these things, pause the video as needed. I'll try to spell it out in words, okay? Part E, give an example of a sequence with the following properties. An is bounded below, an is unbounded above, limit as n goes to infinity, a sub n does not exist. So for these, you probably want to make it as simple as possible. So we can just let an be 0 when n is even, and n when n is odd. Okay, clearly the limit doesn't exist. It will be oscillating between 0 and some value, right? It's unbounded above because it's growing. As n keeps getting bigger, this n will keep getting bigger. But it's bounded below because it's the even values are always 0. So it's for sure bounded below. It never goes below 0. So here's an example. Keep it easy. Okay, number 2. Actually, let me show the whole problem first on the other doc. Okay, here it is. Pause the video and try it first on your own, please. Okay, now I'm going to go back to the other doc. We want to determine the interval convergence, justify endpoint behavior carefully. How do we get interval convergence? We first get the radius of convergence by the ratio test. So if this will move, there we go. Okay. Here's the setup. Okay, now I'll go through some of the algebra here. 8 to the n divided by 8 to n plus 1. You can subtract the power, so you have 8 to negative 1, which is 8 on the bottom. Okay, 3n plus 3, we distribute that, minus 3n, that's cubed, or 3 on top, right? There's the n, ln, n, these don't simplify. and there's n plus 1 ln n plus 1, they don't simplify. So that's what happened here, okay? This x minus 4 cubed, I can pull out, okay? It doesn't depend on n, same with this 8, okay? By the way, let me jump to that note first. Hopefully you would agree that x minus 4 cubed inside the absolute value is the same thing as absolute value x minus 4 cubed, okay? This is true, especially because n is positive and it's approaching infinity, okay? So you can think about that a little more if you need to, but I'm going to move on for now, okay? So from here, we can do L'Hopital's rule. It's infinity over infinity. We can do L'Hopital's rule, okay? So we need the product rule. That's what happened here. It's still infinity over infinity, so I did L'Hopital's rule again. Now I could just simplify this to that, okay? This is algebra. And we take the limit here, it's 1. So we're left with this, okay? We're going to take the result of the limit, set it less than 1, and then start solving the inequality, okay? So I'm going to skip through the algebra. You can pause the video to check it out, but x is between 2 and 6. Now we got to check the endpoints, 2 and 6, okay? So we plug in x is 2 into our original guy, and x is 6, okay? So when you plug in x is 2, you would get this right here, and then we start simplifying. That's minus 2 to the 3n, okay? Which we can rewrite as negative 1 to 3n, 2 to 3n, negative 1 to the 3n, we can rewrite as negative 1 to the n, and this is the same thing as, yeah, 8 to the n, like 2 cubed, yeah, 2 cubed is 8, okay? And then 8 to n's cancel, so you're left with minus 1 to n over n ln n. We can use the alternating series test here. It's a decreasing sequence, and the limit is 0, so it converges by the alternating series test. Check the other endpoint, x is equal to 6, go through the algebra, and simplifies to 1 over n ln n. We can use the integral test to determine the convergence of this, okay? It's a positive and decreasing sequence. I didn't show the work for that, but at the very least, you should state it, okay? That's the condition to use the integral test. And we do the improper integral as infinite, so it diverges by the integral test. So therefore, remember we started from 2 less than x less than 6. Well, we found out it converges at x is negative 2, so we're going to include it. But it diverged at x is equal to 6, so we don't include it still. Okay. Pretty typical problem for that. Okay, now to answer this part, the 12th derivative at 4, this is a very standard problem. This is a power series centered at 4. So when we plug in x is 4, a lot of things would go away. Let's go back here. Right? When we plug in x is 4, it'll be 0, right? So in the expanded form, a lot of things would go away. Okay? And okay, I believe I explained this slower in the Princeton practice problem set. So if I remember, I'll link the video. But basically, you want to find out if there's an x to a 12th term, first of all, inside in our series, which there is. That's what when n equals what? When n equals 4. That'll be x minus 4 to the 12th power, right? So we need that coefficient in front of the x to the 12th term. Okay, so that's why we found that n is equal to 4. Okay? Okay, let me go back again. Sorry for all the scrolling. When n equals 4, then we would have what? 8 to the 4th times 4 times ln 4 on the bottom. So it's 1 over that guy times x minus 4 to the 12th power. So we want to take the 1 over this number. Okay? And in addition, when we take 12 derivatives, there's going to be a 12 factorial present. So when we do the power rule 12 times, it'll be what? 12x to 11th. So then next derivative will be 12 times 11 times x to the 10th. Next is 12 times 11 times 10 times x to the 9th. So you can see how the 12 factorial is going to come about, hopefully. So therefore, that's why these questions are really easy. The 12th derivative at the center of the power series 4 is we need a 12 factorial, and we need the coefficient out in front of the x to the 12th term originally, which is this. So that's our answer. Don't bother simplifying. Even I don't know how to simplify this, especially because if there's ln 4. Okay. Okay, let me switch back to the one for number 3. Okay, we're going to find a Maclaurin series for this guy, and we're going to evaluate this guy. Okay, go ahead and try it first on your own. So most of the time, you don't want to take derivatives to find the Maclaurin series or Taylor series. You probably want to start with something you know and just manipulate it from there. So for example, this is probably the way you would want to go about it. Let's start with 1 over 1 minus x equals summation as n goes from 0 to infinity, x to n. You should have this one memorized. Okay. Now, we want to start making this look like this. Or more, I guess more like this, look like this. How do we do that? Well, I can replace the x with x squared. So I get x to 2n over here. Okay. And I can remember differentiate and integrate power series. So I can just integrate both sides. This side I will leave alone for now. But if I integrate this side, we just do the power rule. It's x to 2n plus 1 divided by 2n plus 1, which matches right there. Okay, so our function f is this guy. Let's just find the integral of this guy. Okay, so hopefully you see my thought process. I first made a power series that look kind of close to this. And then I remember I can differentiate integrate power series. So from here, I just integrated because I know how the power rule works. The power rule looks like that. So that's why I integrated. And now our function is this is this exactly on the left-hand side here. This is the power series we want. And the function is the left-hand side. So we now just need to integrate this left-hand side, which we can do by partial fraction decomposition. I did not show the steps here, but the coefficients after you do it would be half and half, okay? By the way, I think I said this in some other video. I don't remember which one, but whenever you have factors that look like that differ just by the sign, usually the coefficients are same or like symmetric. It'll be like half and minus half, something like that. Just a little tip, okay? So if we integrate, oh, we'll get this. So I'm going over kind of quickly, but this is how we do it, okay? Now, how do you find C though? In the series over here, okay? Or I guess we can even just do, what's f of 0? It's 0, because when x is 0, it's 0. We're summing up zeros, okay? So, we can find that c is 0. Or I guess over here, the first term is when n equals 0, so first term is x, so that means c is equal to 0, okay? So you can think of it either way. I prefer actually the way I just orally explained it, not what I wrote here. But what was I saying? So C is 0, so then this is our solution, or you can rewrite it like this by properties of logs. I don't think this is necessary, but it's a cleaner form if your professor likes that. Okay. Or not your professor, maybe your grader who's picky might want this as well. Okay. Now this one, we're asked to evaluate this guy. Let me actually even, it's bigger. Okay. So if you pay attention, this looks really quite close to this guy. And actually, this is a multi-part problem. We probably want to use the answer from part A to help us in part B. Okay. We just need to rewrite this 1 over 4 to the n a little bit. Okay. Okay, let me go back here real quick. This is the power series from part A. Okay. Let me just copy paste it actually to explain it a little better. Okay. Okay, there we go. Now that's all in one place. Okay. We want to use the answer in part A, but how can we do that? So you can see how it looks similar if you paid attention. Okay, so basically, that's why I said over here, 1 over 4 to the n must be the x to the 2n plus 1 if we ignore this half first, okay? We could incorporate this half, but I chose to ignore it first, okay? So that's what I said here. That 1 over 4 to n must be x to 2n plus 1. So with some algebra, we can rewrite it as 1 over 4 to the n equals 1 over 2 to the 2n, because 4 is 2 squared, okay? Which we can rewrite as half to the 2n. 1 to 2n power is still 1, okay? So now a plus 1 is the only thing different. Can we make it appear? Well, now we can use this half actually to our advantage. So that's why this is how I thought of it. But maybe if we incorporate this right away from the beginning, you don't have to do this extra thought process over here. But this is, again, how I approached it. So as I was saying, this doesn't quite match x to 2n plus 1. It's 2n power, where x is half. It's 2n. So what can we get this plus 1 magically? Well, we can incorporate this half. That's what I'm trying to say. Okay, so the entire series, this guy can be written like this. X is half. Okay, hopefully that's clear. So then, what does that mean? That means we can evaluate this by just f of half, which we found in the previous problem. F of x is this, so f of half is we plug in x is half. So that's half ln 3. Okay. This, to be honest, is a very typical type of problem where the professor challenges you to pay attention to what you did in the previous part and you want to use the answer in this part. Otherwise, how would you evaluate this? I would have no idea how to evaluate this. It's not a geometric series, and it's not a Taylor series like e to x, sine x to cosine x that we know. We can also find the sum of because we have this power series memorized. Okay, so we got to use the answer in the previous part to help us out here. Number 4, find the fourth order Taylor polynomial for a centered at 0 for this guy. And then part B, let f of x be sine x plus cosine x, find r greater than 0 such that this guy was equal to 1 over 10 to the fourth for x is in the interval minus r to r, where t3 of x is centered at 0. Go ahead and try this one, if any of that made sense at all. Okay, so I'm going to right away say that part B is a very bad question. If you're not new to this channel and you've seen previous videos of mine, I've complained about poorly written problems before. So I'll go over why this is, again, a poorly written problem in a bit. But let's go over part A first. So if we're going to find the fourth order Taylor polynomial, it is possible to just take 4 derivatives and get the Taylor polynomial from there. But it's going to be a mess because we will need to use the product rule a lot of times. So I kind of don't want to do that, but it's doable if you want to do that, okay? Instead, maybe let's find the Taylor series for arctan x and e to x over 2 separately and multiply them together, okay? So for e to the x over 2, let's do the easier one first. Let's start with e to the x. Let's have this memorized, okay? So e to the x over 2, where there's x, replace it with x over 2. Okay, so we can even do term-by-term representation, something like this. Okay, we expand it out. Now for inverse tan x, if you don't have this memorized, I also don't have it memorized, we can quickly derive it. We start with this guy again, 1 over 1 minus x, like in the other problem. Okay, we replace x with negative x squared. Okay, so that becomes 1 over 1 plus x squared on the left-hand side. Okay, and then we integrate because the integral of this left-hand side is arctangent. Okay, and again, we can note that c is 0 because arctangent 0 is 0. We know that. Okay, so arctan, if we expand term by term, it looks something like this. Okay, the reason the term by term representation helps here is because, again, we only need to get up to the fourth order Taylor polynomial. We only need the fourth degree term. So when we do the distributing and all that, it's easier, of course, when it's in expanded form instead of trying to multiply this with this. It'll be kind of hard. Okay. It's doable, but I probably wouldn't do that. Okay, so we multiplied to 2, that's what I did here. And as I said, we only keep up to the 4th degree term because it asks for the 4th degree tail polynomial. So do the distributing and all that, and only keep up to x to the 4th. Okay, and we simplify, you get this guy over here. So you can definitely pause the video to check out the math and all that. Okay, so now let's get to part B, the bad question. Okay, first of all, it's not good because the professor assumes that you know this type of notation, which in my opinion, you should, but it's still, in my opinion, a big ask for the professor. Instead, why didn't he just say like minimize the error or something like that, which is exactly what I'm going to point out in a bit. Okay, but anyway, this is the remainder. And so it's probably related to Taylor's inequality and all that. Because you want the remainder or the error to be less than or equal to something. This 1 over 10 to the 4th. This is what this is all about. Okay. So, and he assumes you know what T3 is also. But anyway, so if you don't know, T3 is the third order Taylor polynomial. Okay. So let's find that first for our function f of x equals sine x plus cosine x. This, we can just take derivatives. Okay. Third order Taylor polynomial, we need up to the third derivative. Okay, I took one more though, because if you remember for the Taylor's inequality, the remainder theorem and all that, we need one more derivative. So I took it right away. Okay, but for the Taylor polynomial, we only need up to the third derivative, and that's why I evaluated up to only the third derivative. Okay, so we can find the third degree Taylor polynomial to be this over here. Just use the same formula for the Taylor series, but you don't go up to infinity. You only go up to the third degree term. Okay, so that's this stuff. Again, pause the video if you need to check your work or see how I did it. Okay, now let's start using Taylor's inequality. Whoops. I don't know what happened there, but okay. Actually, that's fine. Sorry about that. Okay. So what does Taylor's inequality say? The maximum error is m over n is the nth degree Taylor polynomial, so n plus 1 factorial. The center, or yeah, the center to the n plus 1, so 3 plus 1. Okay, which if we simplify, it's m times x to the 4th, absolute value x to the 4th, over 4 factorial is 24. Okay, and what is m? M is the maximum value of the 4th derivative of x. Okay, we're going to restrict our analysis to this interval from minus r to r. Okay, so when is the 4th derivative maximized? That's why I took the 4th derivative, because we need the 4th derivative for Taylor's inequality. When is this guy maximized? Actually, before that, sorry. What was I doing? Okay, give me 1 second. I need to review what I wrote real quick. Okay, so there's 2 things we want to maximize. This, the 4th derivative, and also this x to the 4th. Okay, our interval is from minus r to r. So when is this guy maximized? This piece over here? It's when x is equal to r. Hopefully that's clear. Okay. Now, what about this m? So when is this 4th derivative maximized? This is what I was trying to get at before I got confused by the sequence I wrote these things, okay? So when is this maximized? Well, we don't really know what minus r and r is, but let's keep it easy. This is maximized when it's the value is square root 2, because this would be square root 2 over 2, this would be square root 2 over 2. We call the unit circle, okay? Or we call the curves of sine and cosine. Sine would keep increasing, but cosine would be decreasing, even from 0 to pi over 2. Just imagine that interval. Sine would be increasing, but cosine is decreasing. So there's kind of like an inverse relationship. But at the sweet spot when x is like pi over 4, that's when both are square root 2 over 2. So it will be maximized when both individually are square root 2 over 2, which if we sum it up, that's square root of 2. Okay, by the way, pi over 4 is kind of far from the center of this power series, which is 0. It's not 0, right? But it's relatively close enough still for our analysis. Okay, this is why this is not really good. Great problem. Okay, but that's we got to consider that m will be the maximum it could be is square root 2 over 2. Actually, it will always maximally be square root 2 over 2, no matter no matter what the x is. Okay, because these curves are periodic. Okay. Therefore, hopefully that made sense. Therefore, we plug in our maximum value of x to the fourth, which we said was r, and the m we just found, which is root 2. Okay, so root 2 times r to the fourth over 24 is less than equal to, this is what Taylor's inequality says the maximum error would be. We need it to be less than 1 over 10 to the fourth. That's what the problem said. So what's the possible value of r that would make this happen when r is 1 over 100, for example? Okay. And exactly after we wrote this inequality, you can hopefully even see why it's a terrible question. You can pick any value of r that would make this inequality true, like 10 to the minus 15. Okay. So there's lots of possible answers for this. And this is a grading nightmare for the grader and professor and the TA. So whoever's checking the exams, grading nightmare. A better question the professor should have probably asked is what's the largest that r can be such that the error is less than 10 to the negative 4. And actually, even if he asked that, he did post his solution. His solution is not correct because he said that the maximum value this could be, the sine x plus cosine x that I explained, he says less than or equal to 2, which is true, but you overestimated it. It's never going to be more than 1, actually. Okay, so it's more precise, as I explained it, it's less than or equal to square root 2. Our error estimate or our maximum error estimation, is better since I gave a stricter value. He gave something that's true, but it's a more relaxed value. So the error estimate is going to be worse. It might still be within the required limit or whatever, but it's more, it's he's allowing more error basically. Okay, so I'm quite surprised that he made this fundamental error over here actually. But anyway, hopefully the thought process of how to approach this kind of made sense though, right? Regardless of the fact that this, in my opinion, was a terrible question. Okay, terribly written question. Really not uncommon that professors write not good questions on their exams. But anyway, moving on. Number 5. You're going to compute these. So go ahead and try these first on your own. Okay, these are actually pretty straightforward compared to that last problem. Okay, so this first one we need logarithmic differentiation is some power of x to some power of x. Okay, it's kind of like x to the x that we need logarithmic differentiation. We can't use the power rule here. Okay, so we take log on both sides, or we let y be this guy. So we take the log on both sides, and then we use properties of logs to move that cosine out in front. Okay, so now we do implicit differentiation. So differentiate ln y, that's 1 over y dy dx. Differentiate this over here, we need the product rule and chain rule. So that's this over here. I won't go through the details. But after that, we just multiply by y on both sides. And that's our answer. Y is this guy over here, right? So that's how I wrote it over here. Okay. For part B, this limit, how do we evaluate it? Was infinity to the 0, I think. So it's indeterminate. So we got to use the technique where it's similar to what we just did. We log both sides. We let y be this function and we log both sides. Properties of logs, we move that exponent out in front. We can write ln x times ln x and ln x squared. Okay. Now let's find the limit of log y. So limit as x pushes infinity of this guy. This we can use L'Hopital's rule. okay, because it's now infinity over infinity. So we can use L'Hopital's rule, okay? Chain rule on top and chain rule on the bottom. Okay, the 1 over x would cancel, right? This 2 and this ln2 are constants. We move it out in front. Okay, so now what do we do from here? This is the infinity over infinity. We can use L'Hopital's rule again. Okay, these 1 over x would cancel again. So then we are left with 1 over 2 to ln x. As x approaches infinity, it's 2 to infinity on the bottom, which is 0. Okay, so the limit is 0, but this is the limit of log y. We're not done yet. We got to exponentiate it back. So the limit of our original guy is e to the 0, which is 1. Very standard problem. Okay, part C. This we can do L'Hopital's rule because it's 0 over 0 indeterminate. Okay, so derivative of the top, you get this. Derivative of the bottom, you get this. You got to be careful of the chain rule. Okay. Now we would still get 0 over 0. So we can use L'Hopital's again. So this over here, we need the product rule. So be careful there. And don't forget the negative over there. Okay. So be careful of that algebra. And the bottom, we also need product rule. Okay. Now if we plug in 0, we will get -1 minus would be 0 plus 2. So -2. The bottom, we get 2 times 1 minus 0. Okay, so we're fine plugging in finally, and that simplifies to -3 over 2. All right. How about the next problem? So some integrals now. Okay, go ahead and try these first on your own. Okay, so the first one, I see as something squared minus something squared. There's an imaginary square root there. It's just to the 5 power, so it's square root and then 5th powered, okay? So something squared minus something squared, we can do a trig sub. We set up a triangle. If you haven't seen this before, I would recommend you go watch my crash course in trig sub video. Okay, so there I explain how to set this triangle up. But basically, we want to after we set it up, we want to substitute everything in this integrand in terms of theta. So we need x. How do we get x? We can get x by secant theta. And then we can get dx by differentiating. Dx is secant theta, tangent theta, d theta. We can get this term as well. We can get it by square root of x squared minus 1 first. And that's x squared minus 1 to half power, right? How do we get that from the triangle? That's just tangent theta. Okay, and then there's a definite angle. We got to change the limits as well. So when x is root 2, or when x, I guess let's start from the bottom. When x is 1, 1 is equal to secant theta. So theta is 0. And when x is equal to root 2, so root 2 is secant theta. That's when theta is pi over 4. Okay, the integral becomes, so 0 to pi over 4. Those are the new limits. This is this guy to the 5th. So tangent to the 5th. X to the 8th is secant to the 8th. Okay, and dx is secant theta, tangent theta, d theta. Okay, that's our substitution. Now we start simplifying. We will get tangent to 6 on top and secant to 7th on the bottom. So from here, I thought to change everything to sines and cosines. That's my preference most of the time. Okay, so that I see that it becomes, well, 1 over cosine to the 7th is the same thing as multiplying by, or dividing by 1 over cosine to the 7th is the same thing as multiplying by cosine to the 7th. So we were left with sine to 6 times cosine. Oh, let's go down a little more. Sine to 6 times cosine. This is a typical trig integral. There's an odd power, or both of them are odd powers. So in this case, it's probably easiest to just make u be sine theta. And du is cosine theta d theta. And then it's a definite angle. We got to change our limits again. Okay, so the integral becomes this. And this is just simple power rule and fundamental theorem calculus after that. So that's the answer. Okay, so multiple techniques used here. How about this next one? Let me make it bigger over here. There we go. It's a rational function, so maybe let's do partial fraction decomposition. We can factor out x from the bottom. Okay, by the way, the degree on top is smaller than the degree on the bottom, so we don't have to do long division. We're good. Okay, so factor out x on the bottom. Is this term factorable? It is. It's a perfect square, actually. It's x plus 1 squared. Okay, so there's a repeating factor, so you got to be careful. What's the partial fraction decomposition? Is a over x plus b over x plus 1 plus c over x plus 1 squared. We got to, since there's a repeating factor, we got to write it like this. Keep our options open. Okay, we do the partial fraction decomposition. I'm not going to go over the details here, but you get that a is 3, c is 2, b is 1. So you can pause the video to check the work out there if you need to. So plug in the constants like that. This first one's easy to integrate. That's just log. This one's also log. This third one is just power rule. So this is our answer. 3 ln x plus ln of x plus 1 minus 2 over x plus 1 plus c. Don't forget the absolute values for the logs. Okay. Determine if this guy converges or diverges. You got to be careful here. This is a double improper integral. Because, first of all, it's clear to most people that it's improper because this limit is infinite, but it's also improper because this limit is 0. We're going to be dividing by 0. Okay? So we got to be careful. We got to split this improper integral up into 2. From 0 to 1, you can pick any number. I just picked 1 for convenience, and 1 to infinity. And here's the limit notation if it's required. Okay? So if both these integrals converge, the original guy converges. If either just one of them diverges, the whole thing diverges. We don't care if the other one converges, okay? All right, so how do we determine the convergence of both of these now? So for the first one, let's do a comparison test. E to the negative x over square root x is less than or equal to 1 over square root x. Hopefully you agree with that. Because remember, where we can rewrite this as 1 over e to the x squared root x. And since we're dividing by more stuff, we're dividing by more stuff, we're going to be, it's going to be smaller in the final value. Okay. So this integral, this improper integral, if we do the math, converges. So by comparison test, this guy converges as well. Okay. Now for the second integral, we do another comparison test. We can compare that our guy is less than or equal to e to the negative x. Okay. And if we go through the math of doing this improper integral, it's convergent. So by comparison test, our guy converges as well. And since both pieces converge, our original guy converges. Number 7, there's 2 more to go, but here's number 7. Determine if these converge conditionally or absolutely applicable or diverge. Justify your answers carefully. Okay, so here are the 3. Okay, I actually don't recall if I answered if they conditionally or absolutely converge. But anyway, I'll do that live if that's the case, if I forgot. Okay, so for this first one, how do we determine the convergence of this? Well, we can actually rewrite this a little bit using some algebra. Square root of 2 to the ln of n. Okay, we can rewrite it as e to the ln of square root of 2 to the ln n. It's a strange way to rewrite it, but it's true. Just e and ln inverses, we're left with what's the arguments. We're back with the original, okay? Why do I want to do this though? Well, properties of logs, I can move this ln n out in front. So e to ln n times ln of square root 2, okay? Which I can rewrite as e to the ln n to the ln of square root 2 power. Now what's e to the ln n? Again, these are inverses, so we're left with the argument. So we're just left with n. We're left with n ln of square root, or n to the ln of square root 2 power. Very strange algebra, but we want to rewrite it like this because now it's a p-series. Okay, P series, right there. P equals ln of square root 2. Okay, so does this converge or does it diverge? Well, it's a P series. P series converge when P is greater than 1. Is this greater than 1? That's now the question to answer. We need to know what square root 2 is. What's square root 2? It's about 1.4. If you're not allowed to calculate, hopefully you know this. Okay, and what's E? E is about 2.7. So ln of E is 1. Why do we care about E, by the way? Because ln of E is 1, so that means P equals 1 if P equals ln E. Okay? Square root 2 is even smaller than E, so P is for sure less than 1. That's what I'm saying here. ln of square root 2 is less than 1, so the series diverges. Okay? Okay, so I didn't answer the conditional convergence of that stuff, but it diverges. Okay? And the absolute value version of this is the same thing. It's always positive. Um, actually, is this even a right limit n equals 0? Because we have ln of 0, which doesn't work. So maybe this should be a 1. Let me actually check right now. Give me a few seconds to check. Did I make a typo or did this professor make a mistake? I did make a typo. There should be 1. Okay. What was I saying? I don't even remember anymore. Okay. I was saying that this absolute value version is the same thing. Actually, that won't be true because ln of 1 is negative. I think it's negative. It's really close to negative. Maybe it's positive. I don't know. Okay. But either way, it diverges. I'm rambling now. It diverges. So next, this guy. There's a factorial, there's exponential. So what's the good test? What's a good test to use? The ratio test. And the ratio test determines absolute convergence right away if the limit is less than 1. If you remember that. Okay. So we do the ratio test, limit as n goes to infinity, a sub n plus 1 times a sub n. We go through the algebra. So n plus 1 factorial is just n plus 1 times n factorial. So the n factorial will cancel with the 1 on top. We're left with n plus 1. I expanded the n plus 2 squared. And then by product of exponents, you have 2 to the 4 n plus 4 on top. Okay, subtract the powers. And clearly, as n goes to infinity, well, this exponential is going to grow so much faster than this linear term, right? So it's going to be infinite. So the series diverges. So maybe that's why I don't recall if I answered conditional convergence or not. They almost all diverged so far. 2 of the 3 diverged. Okay. Now the last one, this guy. 1 minus cosine of 1 over square root of n. Does this converge? Does this diverge? Well, first of all, this is a very not unfamiliar series, at least for me. So I'm going to, of course, try to test for divergence first. Maybe it'll help us. Actually, it doesn't. We take the limit as n goes to infinity, it's 0. So the test for divergence doesn't help us here. So what test can we use? Maybe we can do an integral test, but I don't want to evaluate this integral. Even I'm not sure how to evaluate it right now. So is it alternating series? Doesn't look like it. Not always, I should say. Does it always alternate sign? I think it does alternate sign. Actually, no, it doesn't. So no. Ratio test we probably don't want to use. It's hard to do the algebra. Root test is not the whole series to n power, so not that. So maybe a comparison test. Why don't we try comparing with the harmonic series? Okay. So when you're stuck, usually you want to pick to compare with a series that is close to this, or if you're really out, just pick an easy one like the harmonic series. Okay. Maybe you'll get an idea, even if it's not the right one to pick, maybe as you go through the limit comparison test or comparison test, whatever one you should do, might get an idea as to a better series to pick as you go through the math. Okay. So limit as n goes to infinity of the harmonic series over the series that we want. I rewrote this as n to the minus half power. Okay. We can do L'Hopital's. So that's what I did here. We start simplifying. These minus signs would cancel. Let's divide by half is the same thing as multiplying by 2. And you can do properties of exponents, subtract these two powers. That's minus half. Yep, okay. So we can still do L'Hopital's because it's still infinity over infinity, or 0 over 0. Okay, either one. Then we can do L'Hopital's rule. So I didn't even bother to take the derivative. Notice I just wrote that guy prime. Because for the bottom, we need a chain rule. It'll be cosine of n to minus half times n to minus half prime by the chain rule. These would cancel. You're left with this. And if we evaluate the limit is 2. Okay, so by the limit comparison test, since we compared with the harmonic series which diverges, our guy diverges as well. So that's why it all diverged. That's why I don't even recall answering absolute convergence. They all diverged. All right. And now the last problem. Let n be greater than or equal to 2, be an integer. Use integration by parts to prove this reduction formula. Okay. So these are the best types of problems, in my opinion, because the answer is right there. You just got to do stuff to get the answer right on the page. Okay. So, and they even tell you to use integration by parts. So honestly, before I solved this practice problem, I just knew of these reduction formulas. I never used them in the past. But now this became a practice problem, and now I had to derive it from scratch myself. Okay. And the hint was integration by parts. So how would you use integration by parts on this left-hand side? Well, we can rewrite it as cosine of n to n minus 1 times cosine, because it's cosine to first power, right? By properties of exponents, you would add the power, so you get back n. Okay, so integration by parts happens like because it's a product of two things. So I chose u to be cosine to n minus 1. du would be, we need to chain rule, so be careful. dv is whatever's left, v is the integral of that. Okay, so integration by parts, uv minus v du. Okay, so uv, that's right there, minus integral v du. That's right here. Okay, the n minus 1 doesn't depend on x, so I pulled it out. Okay, so from here, again, I never did this before, so that's why I might be showing more steps than I might usually do if I know what I'm doing. But since I didn't know what I was doing, I decided to show more steps. So I just moved, or rewrote the sine squared as 1 minus cosine squared, okay? And the hint was, you want to make it look something like this, okay? So this kind of matches already, right? Cosine to n minus 1 times sine, except this 1 over n. That's the only difference, okay? Now, we got to make this kind of match that over here. So that's why I started messing with the sine squared, okay? Because this matches, but this is extra sine squared. So that's why I started messing with it, okay? So n sine squared is 1 minus cosine squared by the identity. Distribute this to both terms. You get cosine to the n minus 2 minus cosine to the n, okay? If we carefully split up the integral, we would get this right here because this n minus 1 is in front. So it would go to both terms and then split up the integral as well to each of the terms, okay? Isn't this guy what we started with? That's my I, okay? So once I saw this, I'm like, oh, I know what to do. I've done these before, integration by parts. Remember like e to x sine x, those integrals where you call this I as well, and then you move this to the other side. So you just got to be more careful because there's this factor of n minus 1 in front. So you add this whole thing, okay? And then to isolate I just factored. And then this simplifies to just n, and that's how you divide by n, and you get I, which this guy matches what was given, okay? So again, these are the best types of problems because this needs to match what's up here. If it doesn't, then you did something wrong for sure. Okay, and again, I'm being honest that I was doing this for the very first time. I never did this before in my life. As I said, I only was aware of this formula, but I was never taught it, and I never had to use them. So this is really me solving it for the first time. And just by taking strategies, I need to get this to match this up here. So that's how I decided to start touching this guy over here. And then I saw the lights after I did some algebra. All right, that's it for this problem set. It's a longer video than usual, or the usual as in what I've been filming recently, but hopefully this was good practice. And definitely if you made it to the end, thank you for watching the whole video, and hopefully you practiced long as well and got some practice. All right. As I said, this is more representative, in my opinion, of what a typical university level exam could be. There's some more typical problems, or per se easier problems, like where did it go? Some of these were pretty easy in my opinion, very typical, no matter what school you go to. And there's some more difficult ones, like for sure this one was really unclear, this tail polynomial one. And this one is more on the more challenging end because you have to realize to use your answer from part A. Yeah, this is very typical though, very easy also, in my opinion. So this is a good mix, hopefully. In my opinion, as I said, more representative of a typical university level exam because they need to differentiate who gets the A's and the B's and all that. So they mix in some easier problems with some harder problems for sure. Okay. Please give this video a like if this has helped you in any way. And hopefully, if you need to refresh on some of these topics, I probably have some videos on my channel, so feel free to check them out as well. Hopefully see you in some other video in the future as well. Bye.